So in this session, I'm going to talk about basically three things. One is I will cover basically roughly the same topic Van has just covered in the first session, but going into more details, more specifics of how things work. And then I will touch upon a number of open research problems, talking about in the application area, security, and the network. And in the end, I'll briefly go over what the NDN project team has been doing over the last 7 years and give us sort of the idea of the direction going forward.
So I will start with going over more details of how NDN works. And let's just take this application scenario, like a smart home. You have a lot of smart devices, and you use your mobile device, a phone or tablet, to control or communicate with these devices. Let's just take this as an example and see how NDN actually works in this scenario, and then I can go to the details of the mechanism. Say you want to read a temperature, or you want to get a camera feed or turn on a light. In IP, if you do any of this, basically 2 steps. First, you need to figure out where all these devices are. In a sense, you have to figure out IP addresses of these devices. Then you send your packet to that particular device address. So that's how IP works, right? So even though there are many small devices, but still you have to come into the room. You have to say, hey, what is the address of my temperature sensor? Once you get an address, you can send the request. But NDN's way of doing things is you come into a room and you explicitly ask the question, what is the room temperature? Okay. In this room, it's just one hop broadcast. Everybody heard my question, and anyone has the answer can answer my question. Okay. As opposed to IP, comes in room, we'll figure out who knows the temperature. First have to solve this problem. Then go to that particular person, ask a question, and what's the temperature? So NDN is more to the needs of the application and users, because you really don't care where this answer comes from, as long as it answers your question. So it's more direct to the application needs. Then the question is exactly how does this work? Okay. NDN has 2 types of packets. And I'll go over the details of these 2 packets. First is the data packet. So in NDN's view, everything is data, and all the network is doing is retrieve the data. Okay. Therefore, in this data packet, the first thing you notice is there's a field content, basically the payload, and that can be anything. It can be a file, a movie, your camera feed, or the temperature reading, or even the result of executing a command. Say I send a command to the light, say turn it on, and the thing I retrieve coming back is say, oh, the status right now is off. So anything can be the content, and in order to identify and retrieve the content, you need a name. Okay. So that you can ask the question, say, I want this content identified by this name. And in this example, I say, oh, it's UCLA, Boulder Hall, room 234, and I want a temperature at this particular time. Right. This is a very explicit question identifying what you want. And anybody having this answer can reply to you. It can be the thermostat, can be a temperature sensor, can be your home controller, or can be your laptop, which happens just got that data a minute ago. Okay. Then, if you can get the data from anywhere, of course, the natural question is this really the data I wanted, or someone forged the data, or it's a compromised data, or it's a corrupted data? Therefore, you need to have a signature. That signature is signed by the data producer at the moment the data is produced. Say you have a temperature sensor produce this reading. Therefore, the temperature sensor put the name and content in this packet and put its own signature here. with this signature, it binds all of this. And anyone receive that data, verify whether here is consistent and know whether it's produced by the temperature sensor or and there's no changes during transit. The last part is some auxiliary optional information we call the meta info. So sometimes it's useful to have additional information together with the data packet. Here I put an example called a freshness period. It's saying how long this data can stay fresh. Meaning, say maybe after 1 minute, the temperature sensor is going to produce another reading. So there's more recent data after that, after 1 minute, to give you a hint of how likely the data you are receiving is up to date. But this is optional information. Okay? The required pieces are the payload itself, of course, the name, and the signature. Okay. And with that, you can see this whole data packet is a so-called immutable object. In a sense, once it's being generated, being produced, this signature binds everything. Okay. If you change the content, you should also change the name to reflect the changing of the content and reassign. So it becomes a new object. Okay. Therefore, with this, you can see from NDN's view, the whole world is all of different pieces of data. And you can name them even though the content changes over time. It's not really, well, if you look at this, it's very similar to our URL, right? It's like a hierarchical name. But if you think about today's URL, if I go to Yahoo News, the same URL give me different content. Today is this, and tomorrow going to be tomorrow's news. If today I want to request yesterday's Yahoo News page, there's no easy way to do that, because that page remains the same name, but the content changes over time. So there's no easy way to uniquely identify a particular piece of data. And in NDN, we say your name should always reflect this temporal evolution of your content. When the content changes, name changes, and as well as the signature, you get a new object. So in this sense, we call it immutable object, and therefore you can uniquely name all the data this whole world has ever produced and be able to say, oh, I want this particular piece. So this is data packet without any network specific, just the data packet. And in order to get a data packet, you want to send interest to say, I want a particular data. And of course, to do that, you put the name in the interest packet. And here I say, I want to have the temperature reading of UCLA Boulder Hall room 234. Okay. So that's my interest, that's my question to the network. And if everything goes well, of course, the data is going to come back. Additionally, you can put some optional fields in the interest packet to help the network identify the exact piece of data you want. In this case, we have a number of so-called selectors that help narrow down, like if this name is not specific enough, you can put some selectors to help the network narrow down the selection so that it can pick the exact data packet you want. And there's this nonce field is useful when there are multiple people asking the same question. So the name will be the same. But sometimes in the network operation, we want to differentiate, say, oh, these actually are two different instances of the same question. Therefore, we'll put a random number in this packet. Okay. The most common use of this nonce is if I send this question and this packet somehow got looped in the network and come back to me again. By looking at this name and the random number, I can tell whether this is the same packet I received for the second time, so that I know, oh, it's a loop, so I should drop the packet. Okay. Without this random number, you may see the same question, but actually it's not loop, it's coming from different people. With this random number, you can differentiate two cases, whether it's a loop or multiple people asking the same question. The last one is some optional field help the network processing the packet. I put one example that's called interest lifetime. It's saying for how long the consumer is still interested in this answer. If I'm asking for the temperature reading at this moment, but somehow, for some reason, my question got stuck. It never got sent out. Okay. Tomorrow, 24 hours later, it got sent out. But I'm not interested anymore. I'm interested in new reading. So this old question gonna have its interest lifetime expired, and network knows, oh, the question is too old, nobody's interested in the data anymore, so I'm not gonna send the answer back. So these are all this auxiliary information. The most important thing in the interest packet is the name. So there are two types of packets in NDN, interest and data. And the most important things are the names. Now, how does the interest retrieve the data? I put the example here. You have a thermostat which which measures temperature and also control your room setting, temperature setting. You want to get that information on your phone, and there's a data. Okay. If this was IP, I would draw the picture differently. I put this data together with the producer, and I would draw the line and say, oh, you send a request, and you send the answer back. That will be how it works in IP. Okay. In NDN, it's different, because when I send the interest, I don't necessarily have to talk to the producer. The data can come from anywhere. Okay. It could be the thermostat, it could be a temperature sensor, it could be a home controller, it could be from any place. So there's really no end-to-end connection, point-to-point connection per se. It's really production of data at the producer end and retrieving data from the consumer end. And the two operations, they don't have to happen at the same time. They can be decoupled. Okay. Therefore, it's possible there's never a moment these two got directly connected, but still the consumer is able to get the data. Usually the producer will do prepare the data by giving the name to each data piece and also sign it. And if you have too big of data, you top it into small chunks. Each chunk will have its own name and own signature. So it's called segmentation. The consumer are doing a lot more. The consumer send interest, get data, and it's one interest for one data. So if somehow the data here is 100 packets, then over there you need to send 100 interest to get this 100 data packets. Of course, interest and data name, they have to match, and consumer is responsible for all of this stuff. You send a question, for some reason, whatever reason is, you didn't get an answer, it's consumer's job to keep sending, and consumer's job to control the rate, verify the data received is valid, and also detect loss and send a retransmission or explore different network interfaces. So most of the work during the communication is happening at the consumer side. So the whole thing, we call it consumer-driven communication question.
So if I am interested in the temperature data and I'm sending a request for that, so will I get temperature data from any producer and I will have to verify which data is correct? Or I can send in selector some that I want data of only this place, so only I get response from that producer.
So let's say, if I understand right, you say, oh, there are, say, 5 different temperature sensors, and you want reading from only one particular one.
Only my home sensor.
or only your home sensors.
Yes.
So usually in that case, you would name the data differently. The name will reflect its reading from your home sensor. So when you send your question specifically asking the reading from your home sensor.
This is your home and not my home.
Right.
Can't I use selector for that? Or like if I my home I have many sensors, so selector tells which sensor, or it's like names has to be different?
The name. Usually it's the name has to be different.
Okay.
Yeah. So this is basic communication, the sending interest, retrieve data one-on-one, and without introducing any complicated network operation yet. Question?
Why one interest for one data packet?
Because it's a receiver-driven communication. Receiver has to control how fast the data coming to me and which data I want. So you need to have some kind of control. And if you have one interest for one data, that give you the most fine-grained control of this communication.
Well, let's say if I visit the selling.com, right? So I just type selling.com, I expect to read all the news, stories,
Right.
eclipse.
Right.
But in your case, you said I have to, for each image, I listen to the interest.
Right.
For that story, for that video clip, audio, you have to listen to each of
Yes,
them.
yes. So, you can pipeline this interest. So you don't have to send one and wait the answer. You pipeline, so they all happen the same time, roughly same time. And if you compare to you may think, oh, it's so inefficient. But if you think about TCP/IP, in TCP, for every byte there's an acknowledgement number. See, that's a TCP's control, and similar here. The same type of control, flow control, happening in TCP and NDN. It just reverse. In TCP, it's the sender sending the data, and we expect acknowledgement coming back, acknowledging all the bytes. Here, we have the receiver getting the data, but using the interest at a packet level to control the flow. Yeah.
So you name the data like UCLA, then room, then temperature, then timestamp, right?
Yes.
There is someone else who's going to come and he's going to request UCLA, then department, then a room, then something.
Yes.
So is there a way, so because it's not universal, is there a way that we're going to tell it this is the structure of the data? Like if there feedback that we can get?
So it's like two parts of the answer. One is when you design this application, design this temperature and the application retrieving data, you design this so-called naming convention. Like how many components of the name have and each component what it is. Okay? And
What we said is exactly the example that you said is nice. That you said you walk in a room, you don't know, and you're going to just ask. Because it's better than 90, right?
Right.
The problem, you don't know the convention.
right. So
Anybody can, like I can set my convention, somebody else can set another convention.
you should know, you don't have to know the complete name, but you should know like the upper part, the beginning part of that. So you know some of the convention. Like I come in this room, I should ask my question using English. I expect people all understand English. Okay, but in a different country, that will be different convention.
No, I said like, I use the same thing than you, but they're going to add department. So let's say they're going to put UCLA, engineering department, then rules, and Volvo, whatever.
Yeah.
So it's exactly, it's English, right? It's the same thing, I just add another department, which makes sense, but I will not get the answer, right?
Right.
If I just send it like that, like UCLA, then the department. Then
So
the
think
temperature,
think this way. The naming convention is really the communication protocol between the consumer and the producer. So it has to have sort of agreement between these two parties so that you can retrieve the right data. I have a couple of one slide later to talk about name discovery, which is you know the beginning part of the name, and you can discover the later convention, but you cannot just from scratch come up with name of your own and expect any other people understand that. So it's all about name, because you've seen the data format. There's no address in it. data packet, interest packet, they all have names, but no address, no ports. And that makes all the differences in all this application security and network operations, because traditional point-to-point connection, this concept is no more. Because if you don't have addresses, how can you talk about connection or point-to-point communication? Right? It's all about the data. And more specifically, the names, they are assigned to each packet because interest data is packet per packet. So each packet has its own name, and it's assigned by applications, like this. In UCLA, Royce Hall, there's an augmented reality feed, and from the camera and particular video file, particular frame and a chunk. So all the way, they reflect application context. And it's hierarchical, like this. Okay, there are other ideas of making name, for example, just using a single hash, one component, but we use hierarchical name for mainly two reasons. One is in the network, you can easily do this name aggregation. Okay. So you can have /UCLA to cover all the content under UCLA. And somewhere in the router can use this prefix to cover the entire namespace. Another reason is with this hierarchical name that preserve the application context, you have a lot more input when you process or consume the data. So I'll give the primary example later is about the security. How do you actually use the names and to formulate your trust relationship and retrieve keys. Yeah, and of course there's naming convention to avoid conflict, and everybody understand naming convention so you can communicate. With names, we only have names to use. We don't have any address and port. If names are used as what we say, the demultiplexer across layers. Think about it, in the traditional network, there's a packet on the wire, and at the layer 2, they look at the address to decide which host gonna pick up that packet. So that's a demultiplexer at that level. Then layer 3, they look at IP address. And at a higher layer, you look at the port number. So all this address, port, all this as a demultiplexer. And they are really the identifier at each layer. And to handle that, we have manage them. We have to do the address allocation, the port assignment, and we also have to handle the translation between this. How do you translate from IP address to a MAC address? And sometimes you want to translate back and all of this. In NDN, we say, oh, how about just let application name the data, and we use that name, that unique name, as a demultiplexer all the way through. So that gets rid of the dependency on all these addresses and ports, and give you this meaningful demultiplexer at all the layers. And also, especially if you have multiple interfaces or you are moving around, that means your address changes. If you have multiple interfaces, each interface has a different address, or you are moving from Border Hall to Luskin Center, your address is changing. In that case, it doesn't matter to NDN because you still want the same data. It still carries the same name. But it matters a lot to IP type of communication because everything built on top of address and address changes. Therefore, using names has this intrinsic advantage. And also, if everyone understands the convention, it's easy to do the auto configuration and auto discovery. And this is a convention, say there's a local name, this room. If everyone understands this convention, then you come in this room, you say, oh, this room and projector, so the packet only propagated within this room, and this particular projector will answer to my command. In the turns out through our research, a lot of work in designing the application protocol turns out to be designing the naming convention. Okay. Once the naming convention is set, most of the part is done. Okay. Say if I have this smart devices, projector or thermostat, and I have my cell phone or other devices, they're all made by different manufacturers, have different models. As long as they understand the same naming convention, they can talk to each other, they can retrieve and distribute data. Okay. Unlike today, different vendors sell different products, and within their product line, they can talk to each other, but across product lines, they cannot talk to each other. Here, the common language between all these different products or different communication is the naming convention. So the name discovery is how do you know the names, right? If I know the complete name, I send it out, network gives me the data. But if I don't know, how do I find it out? So I give the example. NDN has this native built-in support for that. Usually, you know the beginning part of the name. That's part of your protocol. So I say UCLA border hall 234, and I want temperature. Okay. But I don't know when the thermostat sampled the temperature, because the complete name should have after the temperature should have a timestamp, then the value. Right? So I don't know when this guy sampled. Maybe once an hour or once 5 minutes. Who knows? Okay, I don't know that detail. But NDN allows you to ask a vague question, a shorter name. Say, give me a temperature. I don't know when. Then any data with share the same name prefix can satisfy that question. So in this case, this thermostat can send back a reply, say, oh, you asked for, I'm sorry, I got confused. You asked for this. Now here is one data that satisfies your answer, which contains the timestamp, then say chunk number 1. See, the way the mechanism to support this type of naming discovery is you allow a shorter named interest to retrieve a longer named data. Okay. So interest name and data name, they are not exact match, but you can send a prefix and get a specific data item. Okay. After knowing this, and you see there's a chunk 0. Oh, so you know there's later part of this whole entire data. So I will send the second interest, which I will include this specific timestamp asking for chunk number 1. So this is a little example of how, without any actual infrastructure support, just using NDN mechanism, you can learn this later part of the details of the name. And then you can retrieve all the chunks of this particular data object.
But what if the queries and not is temperature? Does the query still work?
No, that doesn't work. So when it's on the component level, whole component level. Yeah. What's the question?
In this, the data item will be one sampling point, or will it be a collection of sampling points in this kind of query?
Sorry.
Picture is received back. Will it be one sampling point, or will it be collection of sampling points?
So here, I'm assuming this is one sample at this time, but somehow the data published is so big, so you have to cut it into 2 chunks.
So it is like high sampling rate sensors where you have frequency of 4,000 or so. Does it mean that every time you have to query it, or can it specify time range that give me data of past 1 hour or something?
The basic naming doesn't support any range query, or SQL type query, regular expression. No, it just this one-dimensional hierarchical names, and you do the matching at component level. Okay. That's the basic. If you want to build something else, you have to do it as application to build on top of this. Yeah.
knows how many chunks is needed to present.
So in the data packet coming back, part of the data packet, there's an optional field identifying saying, oh, I'm the final chunk, or the final chunk ID is 100. So it's some auxiliary information as part of data packet, so you know when it ends. Of course, you can have other discovery mechanism, like if you are downloading a big file, you can have so-called a manifest, which similar to a BitTorrent. So you have this file, list all the pieces of this big file, and you first download this manifest. So then you know how many pieces there and what are the exact name of each piece. Then you send interest to get it. But that requires you to have actual mechanism to support this manifest, and also require you, for example, you know all the pieces already. Here, this reading could be generated on demand. But with manifest, you have to know the data already there. You already know all the names. Then you put the manifest. So for specific scenarios, they can be more efficient, but it's not a general mechanism can be applied to any case. And here is the basic general mechanism. And depending on the application scenarios, you can use different, and maybe some other naming discovery mechanism.
Is there some reason that you include time as part of name? Like, why don't we include location as part of name? Like that long is also very.
So you can, depending on your application needs, but the timing information is generally you need either timestamp or version number, because most data will change over time.
Isn't it the same with location too? When the sensor is movable, sensor is.
Well, if I move, I don't necessarily, like if I have my slides, okay, my slides, I name it, say, Beichuan.com, some kind of. This name of my slides doesn't change if I move to UCLA or to or to San Francisco. It doesn't change.
Like you have a movable card and this location is changing, so it has sensors, and some application may be interested in that
Right,
card
right.
data only when it's an LA or something like
Yes, so that's what I'm saying. It depends on your application scenario. Yeah. But the timing information or version information, that's, I would say, probably true for most cases or all cases. Now we switch to security part, because remember, every data has the content, the name, and signature. As Vance mentioned, compared to this current IP type of security and NDN security, IP has this secure the connection, right? You have a TLS connection to the server that only tells you you are talking to a Bank of America server, and the data hasn't didn't get any altercation or changes over the transmission. It only tells you that. It doesn't tell you anything specifically about that data. Okay. Once the connection is gone, there's no TLS. All the security properties, the trust you associated with the TLS connection is gone. You download something from your bank and you show it to me, I have no reason to trust this is the authentic document. Okay. NDN saying, instead of focusing on secure the path or the session, you secure the data itself. You have the name, you have the content, you put your signature there. So no matter where you get this content, you can get this content from a stranger you run into outside of this building. Then if you can verify the signature, you know this is authentic data. So that's overall, we call it data-centric security. More specific, if I have this data and this is what I receive, okay, how do I verify this signature? I need the key. I need the key, the public key for this signature, so that I can verify the signature is correct. How do I get the key? In NDN, a key is just regular, just another type of data. Has a name, has its content. So in the part of the signature, there is a field called a key locator. It tells you the name of the key that is used to sign this data packet. And you know, oh, in order to verify this signature, I need to retrieve this key. So you send the interest to retrieve that key. And this is the key as another data object, has a name, user Royce Hall manager key, and itself is also signed, and by the campus manager. Okay. And then you go to retrieve the campus manager key until you reach your so-called trust anchor, like the very beginning your trust starts. Okay. So let's say you already, when I'm a student, I come to UCLA the first day when I do my registration, I get this campus manager key as a public information to everybody. So later on, any information coming from UCLA, I can always follow this trust until reach this key. I already have this key, I can verify signature, this one, that one, and go down. So that's how we do the authentication in the NDN.
So the bootstrapping of trust is outside of the system, outside of the protocol.
Right.
Is it possible to put some primitives in place to try and like address that, or something that down the road there could be, because I mean, like right now, multi-rooted key infrastructures are like the root of all compromise in a lot of ways, and there's like the single root one example doesn't have a mechanism to roll itself over. So I mean, is it worth like investigating some kind of primitives to help facilitate root key rollovers or anything like that, or discovery or bootstrapping or anything?
I mean, this is a very good question, but I'm not expert to answer this. All I can say from the basic of NDN is you treat everything as data, so you treat it. However, the security part you have to put on top of that. Yeah. And here, the NDN trust is multi-rooted, ad hoc. It depends on your own root trust anchor. So this is another picture just showing the previous example. And if we generalize this, we come into so-called trust schema. The trust schema is really just a formal description of your trust relationship. Say, here's the data, and data name has this kind of pattern. For that pattern, you have to be signed by a key whose name has a certain pattern. In the previous case, it's if the data is UCLA Royce Hall and anything, and so it's anything follow that, it has to be signed by UCLA Royce Hall manager key. Okay. If any other key sign it, I don't trust it. Okay. So that's my trust policy. Okay. I can codify, formalize this trust policy into this so-called trust schema. And you can make it regular expression or any other form, so very flexible to formulate your trust schema. And this trust schema basically is a description of your trust policy, can also be retrieved and distributed as a data. You set up camera, and you give the camera its own key as the identity. Then you also give the camera its trust schema to say, if you receive a command from someone, you use this trust schema to decide whether you're going to obey this command or not. Okay. So in this NDN trust security aspect, we really use the names, and it depends on the name, the expressive power of the names to describe the trust policy and retrieve the keys. Of course, this is a basic building block. On top of that, you can add all other security mechanisms to achieve your particular goals. So that's a little bit falling behind. So all the previous one is, we haven't touched anything about network or forwarding. Okay. All the previous one, assuming there's one hop, consumer, producer, how do you retrieve the data and verify the signature. So now let's look at if there's network in between and many nodes, many forwarding nodes there, how the NDN works. So we look at this network, packet forwarding, how does it work? So I want to compare NDN network with a traditional IP type of network from a single node point of view. IP node basically get a packet and check whether the destination is myself, whether like are we there yet, like whether already arrived at destination. If yes, you accept it by passing up through the protocol stack. If not, you check your forwarding table. If there's a match there, you forward it out. That's all IP does in terms of processing the, in terms of packet forwarding. Okay, there's two basic check. NDN, there are a number of important differences. First, we have interest and data. So two different processing flows. Second, when the interest come in, there's no address. So you don't got ask the question whether we are not there yet. You ask a question, do you have the data? If this node has the data, it returns the data. And it's done. Okay. If this node doesn't have the data, you try to forward it. You look at the name and look at your routing table, see whether you know where the data potentially could be, and you forward toward there. So that's how you process the interest. First, check whether you have the data. If you don't have the data, you try to forward it out. Okay. And when the data come back, you look at whether there's any pending interest waiting for the data. You know, if I'm a router, I connect two neighbors, a downstream neighbor and one upstream neighbor. One of the upstream neighbor, well, both downstream neighbors send me the interest. I forward interest out. There's a data come back, satisfy both of them. If somehow another copy of data coming in and there's no pending interest, then I will just drop it. Okay. So data come back, you just look at whether on your downstream anybody waiting for the data. Okay. So this is a high level thing. There are flow of both direction, interest coming this way, data come back that way, and here you got to check the data. You got to have a routing table, and also you got to have a table to check whether there's any pending interest.
Maybe be useful in the upper diagram when the interest goes out the fib, it adds it to the pending interest table.
Yes.
So that.
Yes, that's
kind of a missing piece in that.
Right. That is one part of you have to update the pending interest table. I want to make this simplify this figure, so I didn't put that detail. But yeah, Jeff is right. So we're basically going to talk about those three tables. The forwarding table, it's very similar to IP's forwarding table in the sense it has the it tells you where to forward, has the next hops, and you search this table by a certain key. Just in IP, you search a table by the address, and in NDN, you search a table by the interest name. So if interest name is this, you go through your routing table. The routing table suppose have entries. Each entry lists the prefix and a number of next hops. You find a match, then you look at, oh, this is our next hops, so I forward the interest over there. And the match, similarly, we do the longest prefix match. The main difference between IP and NDN forwarding table, of course, the obvious one is it's name-based, it's not address-based, it's name-based. The second one is usually we have multiple next hops. It's a common case, it's not a special case. We have multiple next hops, and those next hops may point eventually lead you to different multiple data sources. Because the purpose of the forwarding is trying to get the data, and data could be at multiple places. In IP, the purpose is to reach a particular destination, and that in the whole world, supposedly, there's only one destination there. So in IP, the single next hop, that's a lot of cases, and also a lot of cases just lead to one destination. NDN likes to have more forwarding options and forwarding choices. And later on, I'm going to talk a little bit more when we talk about the page table. How do we build the FIB, the forwarding table, or how do we populate it? How do we know for this particular name prefix what are the possible next hops? There are different ways. One is you can do what I call conventional routing algorithm, so link state routing algorithm, which disseminate the whole topology to every node. Then you compute the path to reach particular node. Right? Here, for each node, you don't associate it with the IP prefix, but you associate it with a name prefix. That same algorithm you can apply to NDN. Everything works. Okay? You just replace the IP prefix by name prefix. You can also explore so-called unconventional routing algorithm. One example is this hyperbolic routing. It doesn't disseminate the topology, but rather disseminate the coordinates of the nodes. So, with the coordinates, you do the greedy routing, greedy forwarding. Okay, so get closer to the final source where the data is. Okay? This is possible in NDN because, again, I have to refer to the next slide. I mean the next couple of slides, because in NDN we have ways to get rid of loops. We have ways to get rid of forwarding dead end. So this hyperbolic routing can work. In IP case, sometimes because this getting in the loop or for a dead end, it doesn't work 100%. Therefore, you cannot apply this to IP. But NDN, the data plane or forwarding plane can handle those problems. Therefore, you can take new type of algorithm. And also, in the local environment or mobile or ad hoc environment, you don't have this routing protocol. You can flood your interest. I work in this room. I don't have to run any routing protocol. I flood my interest. Whoever has the answer, give me the answer. Or in the mobile case, because your neighbors are changing. So when you have a question, you flood this question to your current neighbors. Whoever has answer, it come back to you. So this is also possible. So there are different ways to build this routing table, and it really depends on your network environments. You develop your or adopt different type of ways. Content store. That is where you check whether you have the content or not at the network layer. This is possible in NDN because in NDN, when you receive a data packet, it has a name. So if someone else later asking for the same data, you know it. In IP, just look at an IP layer, IP header, you don't know it. Even everyone in this room are watching the same YouTube video of solar eclipse, but from the network point of view, these are separate connections to the server. But in NDN, if the router here handling all the requests are the same thing, it can recognize that because every request carrying the same name. Therefore, we can cache the content, and it's transparent. It's in network everywhere you can do it, and it's on the path of your interest. Of course, you get all the benefits of the caching, reduce server load, reduce response time, and so on. One thing I want to emphasize is, even if you only cache this packet for a short period of time, say at time scale of RTT, it can still be useful when you try to recover from a loss. Think about TCP type of thing. You send a packet, you wait for the ACK, you don't see the ACK, it times out, then you retransmit it. Okay. That's really about the RTT timescale. Even that timescale, if the data is cached somewhere in the middle, you're going to retrieve it from where it was lost, not from all the way from the original sender. Okay. So that will help. And or if you move a little bit, you move from this building to that building, and you ask for the same content, it doesn't go all the way to the server in San Jose. It goes to your UCLA local local router. So even short period of time of caching can still benefit the communication. Okay. So the third table, and also very important, called pending interest table. I don't have animation here, but I just illustrated the flow. We have two consumers here, we have a producer here, and we have router in the middle. When the first interest arrives in this router and this router forwarded, it will write a PIT entry in the table saying, I have forwarded this interest, and the one requested is of this interface. So later on, when the data come back, I know it's this interface I should send the data out. I don't send data to this interface. Okay. If two of them sending the data interest asking for the same content at the same time, I only need to send one copy over there because they have the same name. They're asking for the same content, so there's no need to send multiple requests. I just send one, and data come back, it will be forwarded to both consumers. So the PIT entry really remember the name and the nonce of the interest, and also the incoming phases, so that when data come back, it can follow this incoming phases and go back to the requesters. Okay. So that's the purpose of the PIT, to get data back to the consumer. Okay. If you don't have this, think about how does data go back. Because data only has name in it. If you do the name-based routing, that routing always points here. You cannot get data back. You use the PIT to get data back. Question?
This interest table is absent in TCP/IP. So adding here, does it add any overhead to the protocol?
It is. It is overhead. It is actual states inside the router. Okay. But if you look at, if you look at not just TCP, but all the other functionalities we try to stuff into the IP architecture, you're going to realize actually they all end up with a lot of states in there. And the common thing is this. For example, this is multicast. With PIT, you support multicast natively, in the sense the operation of unicast and operation of multicast has no difference whatsoever in NDN. In IP, if you want to support a multicast, you have to put more states in the routers, as well as invented a whole set of protocol to handle multicast stuff. And they are not compatible. They're totally different thing. In NDN, unicast is just a special case of multicast. All the operations are the same. You also use this to suppress duplicate packets. So if there's a loop, because you remember you have sent this packet before and it loops back to you, you know you are seeing it for the second time and you drop it. So there's never a persistent loop going around, around, around. In IP or Ethernet or whatever the traditional network, your biggest worry in the forwarding is loop. So that's why with the Ethernet, you have to reduce the topology in a spanning tree. And in the IP network, you have to do the routing protocol, have to make sure all the forwarding towards the destination is a tree, so there's no loop. In NDN, you have this built-in capability in the forwarding plane to detect and drop the loop. The third benefit is, compare these two. This is NDN and this is traditional network. In NDN, every hop between this computer and this router, this router, this router, every hop, you have interest, you expect data, interest, expect data. So if something goes wrong, say something goes wrong here, you send the interest, you didn't get data. You know that because you expect data come back within a reasonable amount of time. Link fails, packet drops, or somehow this router misbehaves, anything that doesn't give you the correct data back, you know it. So this is what we call a closed loop feedback. In IP, you forward a packet, you are done. You're done with your job. If the packet got dropped, you don't know. You don't get any explicit notification. You don't get anything. If you care about it, you have to add actual mechanism, like a keep alive message, sending back and forth, or periodic some announcements, or some monitoring monitoring traffic to monitor this link. And if it's not a link problem, it's congestion drop, you have to monitor the delay or some other or sequence number. So you get a lot of other mechanism, try to discover or find out whether something goes wrong. In NDN, every hop, you have this loop back. You have this feedback loop. So then you know not only whether it works, you also know how well it works. You know, I have two options. I send interest to both, and one give me a data after 10 milliseconds, the other one give me data after 1 second. So I know the first option is my better option, so future interest can go there. This is all possible because you maintain the same state in the router and give you all of this benefit. And to further take advantage of that, well, we have a concept called forwarding strategy. This forwarding strategy really is take advantage, say FIP has multiple forwarding options. Okay, this multiple forwarding options, you could take multiple forwarding options, and it could be part of a loop or in some cases, but it doesn't matter. And you have PIT, enables your fault detection and performance measurement. So now the router sitting in the middle with multiple options, and you can try each option, and you get the feedback. So you know this one works well, or you know this one works well, and what's the delay, what's the throughput. Then you can put more like a smart decision process to decide at each hop where to forward. Okay. And this forwarding strategy can be customized for different type of data. Say, if data with a slash video, I will try to choose this type of path. If the data type is, say, IoT, I'll try to go to a different type of path. Depending on the data, you can customize your strategy, or depending on your network environment, whether it's wireless, whether it's wired, whether it's a lossy packet, or a lossy network or not. So you can have different strategies to suit different communication environment and data type. So as a summary of how this NDN works, important thing is the data is identified by names and signed by producers. So that gives you the immutable data object that a consumer can retrieve. And in retrieving the data, the consumer needs to send interest. And the DataCentric Security and trust schema. That's how the consumer, after receiving the data, how they verify and trust the data. And in terms of network forwarding behavior, we have this data plane that is stateful, maintain the PID states, but that gives you a lot of benefits in terms of caching, multicast, and forwarding strategies. All of this form this underlying mechanisms to make the whole NDN work, so that when you walk in a room or you go to watching a video, you can just ask the question, ask for the data you want, and network give you that. So any questions? Yes.
I don't know if you explained this. Do you consider any privacy model in the network when your interests are forwarded and routers know what you are looking for? Does it exploit the privacy of the consumer in any way?
So the router, by default, will not try to understand the meaning or the semantic of the names. It just treated the name as a bit of strings with this different components and try to do the match. You could look into the actual names and try to figure out, oh, this guy is watching a video. Okay. If you want to protect your privacy, you can sort of encode your names or use different name, try to hide your intention. Okay. If I use an analogy, it's kind of like you use in IP world, you jump to different IPs, try to hide your original source address. In NDN, if you have the agreement with another, with the content provider or with another third party, you can sort of use a totally irrelevant name, but somehow that guy understand and give you the content. So you have to do something on top of the basic mechanism to achieve that kind of privacy.
Like today in system design, there are many content providers which are honest but curious to know about the consumer.
Mm-hmm.
So, does you have anything to protect against that in this protocol?
You mean the ISPs?
Yes.
Well, so the consumer, in order to defend, you consider that as a tag and try to defend against, really the consumer and the sort of the producer has to agree on certain scheme so that you can hide your name in certain way or encoded your name in certain way that ISP doesn't know what you are talking about. Okay. But in many, well,
It's going to be a real issue if there are so many routers in the system and many of them are arbitrarily entered in the system, like which are looking at my namespace.
Well, I think the problem is similar in the current network.
Yes.
It's just the solution will depend whether you are doing NDN or whether you are doing IP. The solution will be different. But I think the problem is the same, right? Yeah.
In that scenario, if each consumer makes a different name to fetch like a Wikipedia page, a Wikipedia page for UCLA, each consumer makes a different name to fetch that, then how does that affect caching?
Yeah. It's going to break the network.
Name the data networking, name is fundamental. You cannot just make up arbitrary names. and
Well,
then put in the system
in
and
an
hope
agreement
the
with
system
in
is
an agreement with the producer.
Right.
Well, as long as the application is consistent naming, if the cache is kind of semantic from your name, as long as everyone, how the Wikipedia who are actually just repeat pattern matching. As long as
Each
the
consumer is going to, in an agreement with the producer on how to rotate the names, is going to make a different name so that people on the path don't know what they're asking for, but it's going to have a different name each time.
not each time.
No?
If you think about this really distributed coordination, everyone needs to be consistent about how you name a piece of content. So not each time. Each time the coordination will change.
Well, I think it's a trade-off the producer and the consumer they have to make. Like, I see there's different solutions to the privacy problem. If they go with a solution that for every different consumer, the producer will encrypt the data differently using different keys, then you won't have the benefit of long-term caching. Your caching only benefit this retrieval, packet loss, or little mobility. But there could be other solutions, like they just encrypt once, the whole big movie, Netflix movie, just encrypt once, but somehow the access to the decryption key is controlled by some other mechanism, and it's maybe that key retrieval or something like that has less benefit from caching, but the big encrypted movie is shared by everybody. Right. So I think that you can come up with different solutions depending on your target of the privacy property and the network performance property.
And also to add to your answer, there is some sense of obscurity to the ISP knowing your information, right? Because of request aggregation and because of there not being any sense of endpoint, there's no source address. So really your first hop has to be compromised for somebody to know what you're asking for. Other than that, it's just the intermediate routers just store the forwarding port. They don't store the complete address of the source which originated your request.
Yes.
So
Yeah.
there's some sense of obscurity.
Yeah.
there.
Thanks for adding that point. So it's very similar to the onion routing. You know your downstream, immediate downstream and upstream, but you don't know who's the final producer and consumer because there's no address. So in a sense of privacy, is really you match the data with the requester ID. And in the IP world, you know the requester ID identified by the address, and for the content, you do deep packet, you look into the packet, you know what it is. But in NDN, if you don't do anything actual, you know the content by just looking at the name, but you don't know the address.
But in that, don't we have the nonsense base to verify that it is coming from the same consumer, the request is coming from that?
Well, you know it's the same packet. So you have the name, you have the nonce, you know that it's the same packet, but you don't know who actually sent it and where it come from and how far away it from you. So, yeah. Any more questions? Okay, so I believe I'm sort of running out of time, so I will skip the next part and go directly to the third part. So next part, I was planning to talk about some open research problems, but I think the slide's pretty self-evident if you guys understand how NDN actually works, and you can really go read those slides. But just in a quick summary of the second part is right now because NDN's new network architecture, in a sense, you don't have anything like point-to-point conversation as before. Before, when we design application network protocol, you always think about sender, receiver, client, server. And now there's no such thing. And all you can think of is there's a data. Somebody some time ago produced the data, or maybe can produce on demand, and you want to retrieve the data and verify and consume the data. So a totally different model. That requires rethinking of security, application, and the network. Usually, when I look at a research problem, I look at three different angles. One is, how does NDN actually work in this particular environment? Okay. Without addresses, only with the name, how do you make it work? And the second one is, how do you take advantage of NDN feature to make the application better? And the third one is, okay, this is all good, but NDN has its own overhead because it's doing more than IP, and it matches closer to the application needs. Then how do you optimize the performance? So really, these are three angles I look at to each environment. And in our research, we focus more on the so-called infrastructure-free environment, where you don't have the wired, fixed, reliable connections. You have mobile, disruptive, delay-tolerant type of environment, and how to make NDN work and take advantage in those environments. Okay. And I will skip the details of this and go directly to the third part is what we have been doing as NDN project team in the last few years. We spent a lot of time, especially Jeff's group, Lisha's group, Alex, developing a lot of applications. Because we believe nobody really wants a new architecture or new network design just for the sake of network. right? You want a network, new network on different design because they make your application better, or they enable new applications. Our current focus is on the mobile edge computing, Internet of Things, or navigable media, this type of ad hoc local communication, but take advantage of NDN's feature that you are not locked or depending on your current address or port number. You can move around, your connection may be up and down, your content may change, very dynamic, but you always use a name as a rendezvous, as a way to achieve your goal rather than translate to address. We also have done a lot of other applications. You're going to see the demo of mobile health this afternoon, and we have applied to the building automation and management. Jeff and Peter, they did video, audio conferencing. So a lot of applications, we try out the NDN design and also give feedback to the network design. Of course, on the network side, we do a lot of mechanism design, and we gradually evolve our packet format, protocol spec, and a lot of things we mentioned and we covered in the research problem, but you can look at this later. We also have a big emphasis on running code together with our application development. We had the network forwarder that basically implemented the fundamental NDN protocol, and we have a lot of libraries for different language binding and different functionality, and a number of tools. And they run on regular Mac, Linux operating system, as well as a number of IoT platforms. We also have simulator, emulator, the global testbed, which John gonna demo in the afternoon. And all the code are open source, and we really welcome contribution from the community. And there's also research community growing over the last few years, specific for NDN. We have NDN-COM as annual meeting. Somehow we didn't manage to get this 2016 because the scheduling problem, but we get it 2017 at a different time. So we have successfully had 3 NDN-COM. There's also information-centric networking, a bigger umbrella. ACM has a new conference for that. There's a bunch of workshops. IRTF has a working group, research group, both academia and industry people interested in this. So there's not just a few universities working on this, but a broader community is forming, and with the momentum going to make NDN research closer to the reality. Our website, all the information there, and I believe the slides will also be available. And welcome to join the mailing list or send email to me or to anyone here for your questions. We have different mailing lists, some for the general NDN questions and some for the code development. We're also going to have demos and code-based overview this afternoon, I believe, in the same room. So don't miss that. It's going to show exactly the example of how we do the applications, how the trust model works, how the network handles the dynamics, and so on. Okay, that's very interesting stuff. So I think that will be my talk and questions. I'll talk about research open questions in 3 areas. One is the application, then the security, then the network. Okay. For the application, the biggest thing is the namespace design, because most of work in application designing, in today you would design the communication protocol, but in NDN it's really design a namespace. And usually a namespace, you can have a long name, many components, and you want to put different things in it because the same name is being used by both application and the network. A common case, you have the initial part to help direct the interest forwarding, so how to reach the data. Then this high-level identifier, for example, the living room, the temperature, so high-level identifier of the data. Then more detailed, like what type of data this name is naming, right? Whether it's a key, whether it's some kind of MIME type or some kind of other type of data. Then the last part is some suffix like sequence number or version number or segment number, those details. Those details could be automatically generated and learned, but the design part usually is on what information goes to each part, and really you have to customize this for your particular application scenario. We struggle in a number of applications how should you name it. Say if you want to name all the devices, smart devices in your house, okay, you could name it by where you put them. Say living room light number 1. Okay. You could also name it, say, by the manufacturer and model number, right? Say refrigerator, Samsung refrigerator, or a model number. So you actually can name different ways, and depends on what kind of data you are dealing with. And you could have multiple names for the same data. Then you have to also publish the sort of the link to link all these names. Say, oh, this name and this name actually point to the same thing. Okay. So there's a lot of flexibility, design room when we design applications. It's hard to say what is the single right way to design application, but we are hoping by doing exercise on a number of cases, we can come up with some design patterns that people can use in future applications. Access control, as I think we touched a little bit on privacy discussion, right? Access control, a lot of times, in today, that's one server controls the data dissemination and the access control, who can download it. But in NDN, your data may not be located in the server at the same time, because it could be cache, could be located some repository or some other places. So you really want to have a mechanism that really goes together with the data. So one general approach is you encrypt the data. So everybody can download the data, but they cannot see what's in the data, what the data is. It's encrypted. And then you somehow come up with a mechanism to control the access of the decryption keys. That would be a lightweight. In terms of network, that's a lightweight. But in terms of security, that's the most part of the security mechanism. Okay. You can try just everybody has its own private keys, or you can try there's a group key and you control and manage the group keys, or you can try the attribute-based keys. There's a lot of options in the design space. DDoS attack. That's really a headache in the IP architecture. And we know DDoS attack for many, many years. And we don't see very good solution. And every year we just see more and more or more serious report of these instances, right? Earlier this year or later last year, there was say, oh, there's huge DDoS attack from a lot of IoT devices overwhelm website or blog site. Right? NDN is different from IP. IP, you get a packet, you throw at the destination. That's IP designed for. So if there's denial of service attack, you throw a lot of traffic at destination. It's hard to fix it because architecture fundamentally was designed to just push data to the destination. NDN, the receiver has to ask for the data before the data can come. So by default, if I don't ask anything, my neighbor should not send me anything. Okay. If my immediate neighbor misbehave, send a lot of things on my wireless link, I can't do anything about it. But arbitrary, some random guy out there across the globe cannot send a lot of traffic, overwhelm my website. Okay, that's just impossible in NDN. But you say, oh, I may do the DDoS attack by sending a lot of interest. You can send interest. Right? Now, with the interest, there are two cases. If the interest you send is actually asking for existing data, you send me an interest, I give you a data. You send me 1 million interest, I still give you 1 copy of data because it's automatic multicast and caching. So it's possible you send me a lot of interest, but it's very hard to generate a lot of traffic load at my server if all this data can be satisfied by existing data. Okay. The only really possible way to do the DDoS is you send a lot of interest, and those interest names somehow match my prefix. Okay, they all have UCLA computer science prefix, so they all coming to UCLA computer science. But the details, they don't match anything. Therefore, caching doesn't work, multicast doesn't work, it's just no return, it just keep coming, all this random object, non-existent, all this interest coming in. Okay. If you do that type of attack, all the routers on the path, they're going to be easily to see this behavior, because the normal behavior is interest coming in, after a little while data goes back. Interest coming in, after a little while data goes back. But if you have this type of denial of service attack, the pit table in the middle will build up quickly, because all the interest coming in, they don't pull back legitimate data. So they just build up the pit. And the router can easily detect, say, oh, this guy keeps sending me a lot of garbage interest. Something goes wrong. Okay, I don't know why, but it just consumes my network resource without doing any useful work. I will cut this off, or I will reject, or I will reduce the rate. Okay. So you cannot prevent someone doing that, but you can detect it, and you can have some countermeasures. And that detection can be done anywhere in the network or anywhere the attack traffic becomes significant. It doesn't have to be at the server side. The routers in the middle can do that. Okay. So in this sense, NDN architecture is much more resilient than IP network, because the fundamental philosophy is different. It's not by default you can throw anybody and anything, any garbage to anybody. It's by default nothing comes in, and you have to ask the data you want, then that data come back. Okay. In this sense, it's much resilient to the DDoS attack. Another type of thing is content poisoning. Say, I send interest, I got data, but it's my neighbor deliberately forged a fake data and gave it to me. As a consumer, I always verify the signature, retrieve the keys, the certificate, eventually verify it's a legitimate good data. If it's bad, I will be able to detect it. Okay. It's not the case for the router by default, because if the router verify and every data, it's just really a lot of workload. Routers just for performance reason, you don't want the router to verify every packet. Therefore, there's a question of, what if a consumer receive a bad data and want the router to say, oh, hey, by the way, last time you sent me this bad data, please kick this bad data out of your cache and use another path, find me different data. How do we do that in a secure way? Right? So how does the router trust this consumer telling the router to change this? So there's, and you really, And this is really a balance of the performance. So there's nothing prevent the router to verify the data because all the mechanisms are there. Router can verify the data same way as consumer verify the data. Only for two reasons we don't do that. One is the performance. The second one is sometimes the router doesn't have the policy of the consumers. So what the router sees legit is different as what the consumer sees, right? So we have to solve these two problems and make a good trade-off so you can deal with this problem reasonably without too much sacrifice on other things.
Question.
Yeah, question.
Yeah, when you are getting a lot of unwanted users, how do you how do you know that who is sending that? Who is that? How can you cut off communication? How can you make him stop sending those unwanted?
Okay. I believe Alex and some other people, they worked on this, but the thing is you do this hop by hop. So I don't know who the attacker is, but I know this downstream neighbor sent me a lot of garbage. So I will cut it off or reduce or put a bandwidth limit on this guy. I could also tell this guy, hey, I'm putting this limit because of this. And that downstream can do its own thing to its downstream. Yeah, hop by hop. Hopefully we can gradually push to the attacker. Yeah. This, in terms of network, as I mentioned, we really focus on this instructorless environments, like mobile ad hoc, delay tolerant type network. The fundamental advantage of NDN is we are trying to fetch the data. No matter what the connectivity situation is. In the IP, you have to deal with all kinds of different problems. In terms of mobility, you really want to chase the mobile node. You want to know every time where the mobile node is, so you can send a packet over there. Even though maybe the data you want is available on this neighbor, but somehow you are zooming onto different node and you keep tracking where it is. Or trying to establish a connection between two nodes, but if it's delay tolerant network, you cannot do that, or it's very hard to do that. Or a lot of today's application, or I would say most of today's applications, they rely on the cloud because of convenience. They just using IP. Locally, you have to figure out who are my neighbors, what are their addresses, and then I communicate with them. And they may go down, and next time I have to do the same thing. So the convenience of going cloud is there's a well-known host name. I talk to that guy always on. So it's convenient for my application, for my network communication. It's convenient. But if the cloud is not reachable, then a lot of communication you could and you should do locally cannot happen. You go on a cruise ship, you and your friends have the same social app, and you have the cell phone, and you have the Wi-Fi connectivity. Physically, everybody connect to everybody else, but you cannot use the app because the app was designed to always talk to Facebook server in San Jose. I mean, that's ridiculous. You have everything you need, but just because of this reliance, the communication cannot happen. Or you do have your IoT connection, but after earthquake, after hurricane, those communication got damaged. You don't have persistent, reliable internet connectivity. You only have local connectivity. Then, again, NDN can easily work if you run NDN application, but IP application, today's application, they will have very, very hard time. So we try to take advantage of this feature and work on solve a bunch of issues when you apply NDN develop application, NDN application in this environment. And the issues involved will really be auto configuration, discovery, the security model and mechanism in this local communication environment, and also the routing and forwarding strategy. How you forward, where you forward the interest, where the data is, what data may be available in this environment. All of this are very different from traditional wired internet. So looking at this new type of environment, taking advantage of the basic NDN architecture, and we look into all these research questions. Okay. So I think I will stop at this slide because we have only a couple of minutes, and just want to show the last one, this website, and we have demos and code base overview in the afternoon. Okay. So any questions? Okay, thanks, and see you in the afternoon.